Today we're going to cover by method of undetermined coefficient and up to there because that's the point I done with. I didn't do the variation parameters done yet or Laplace transformation yet. I have it there, but it's not good enough. And I finally were able to cut down my page number so I have some room left. Um, Basically, I don't want, I already talked about multiple times. Anyways, let's continue over here. I wish I can do this on, I have, how Amazon has Kindle? And and then there's paperback and there's hard copy. I know how to do paper and hard copy, but I don't know how to do Kindle because my PDF always gets messed up there. I'm trying to fix that. I don't know how to fix that yet. So yeah, I'll figure it out one day. I just don't know it yet. Anyways, over here you see circuits over here charge. The charge is like this. Basically this is true, therefore you just plug into the original voltage addition question. Luckily it's DC, so this is pretty easy. DC has a constant like boom of voltage, so it makes sense that it would be a linear line. Um, and which it does turn to a linear line. And over here, if you can look over here, uh, if you use method of under this method over here, this thing, you'll find that this doesn't have a Q. So you have to even though this looks like um a zeroth order, it's actually a first order because there's no Q over here. But neither here nor there, you should not be using method of differential undetermined account for this stuff. You can, I wouldn't recommend it. It's like just do the integral to make it first order and then solve it. So much easier than doing weird stuff. Why would you do weird stuff on this one? Especially since I will say if the easier way to solve this with matrix, which we'll learn soon, I would recommend you solve this with matrix actually. I just haven't done it yet. We will one day. Uh yeah, it's gonna be the section, so stay tuned for that. Anyways, over here, falling mass with linear drag. So over here, we're just grabbing one raindrop and doing a force diagram over here. Although there's many assumptions and you have to go to weird fluid dynamics to actually prove that this is true. But it is true for small Reynolds number. And that's why I made this very small for this situation where the viscous flow would work. It's actually a very common question with raindrop, and it does work. It's researched many times. It's not a real life question because I did fudge the numbers to make it look make it unique, but and simple. I think I rounded it down or up. I don't remember, but it's been researched before with raindrops. So over here. You get the integral and then you get a first order equation. I'm not going to the details because this is just basically going to first order because you take an integral of this and you kind of get this already. We did this like 20 times already, so there's no need for me to go any further with this. Now, the method undetermined coefficient is where I'm going to talk a lot more. This actually is something new. Now, I I went a little bit crazy with the first one by giving crazy initial conditions that I regretted doing because it took forever to get a right answer, and I had to whoop out Wolf Alpha for this one, and multiple of them I had to bring out Wolf Alpha because I was like, all right, I need to double check my answers. We start off with this, and then you get 4t plus 1 is our initial. I mean, this is nothing yet now. This is our forcing, but um. Yeah, that's with forcing, right? So anyways, we're going to do with springs a lot because the process is the same if you have a negative. You just solve the homogeneous part as is, which I thought, yeah, I could do that question, but there's no point. I'm not going to make a difference on that thing. Um, I'm just going to solve it. So we solved it. We denote this by YC. So this is actually the initial characteristics of a ODE without forcing. A forcing is like a molder or something that forces it to do something. For a spring or mass, think of it as a extra motor pushing it this way and constantly, which is why if you do in this case it'll break because it's like a linear line. So it'll keep on pushing it and this thing will eventually break. But before that there will be a struggle here. So it doesn't simulate the struggle. So that's something to note. Anyways, we move on here and we have to choose our perfect guess. And our guess is designed by what this is going to go to infinity. It makes logical sense because think of what will happen when this forcing goes to infinity. Well, that would be a first order. So clearly over here, first order was a correct choice. Now that's why we get our particular solution over here. That's why it's denoted by YP. And now YP, you take a derivative of it and a derivative of that to plug into original formula. Why do you do that? Well, think about it this way. You have an end result and you plug it into the original to see that it works at infinity. And if it works at infinity, you need to make it work. Those constants must be still the same. It's kind of what the vibe is getting. Like this is the leading path of infinity. So imagine this thing over here. This is like wobbly, but in the end it goes to a linear line. But this linear line over here must have the same constants. A1, A1, A2. These must be the same. Um, so even at infinity over there, it must be same. So that's why this works. This is why this works. Don't get that wrong. That's why it works. Um, at least that's my understanding of it. I might be, I mean, I'm pretty sure I'm right because it's been a long time since I did this. And actually, my professor actually skipped a method of coefficient. I understand why. It's a numerical analysis. It's not really useful. There's many ways around it. The variation parameter is way more important because of way many different reasons. I know why he skipped it. I just don't like it. I think he should have went with it because we see the rule from alpha use method undetermined quotient first, and then always Laplace transformation. Laplace transformation because Laplace transformation is just better. It is 100 times superior in every way, and I will be teaching that soon. Laplace transformation is number one, in my opinion, in the best way you can think about it. Anyways, I might actually think of getting this book over 550 and I'll be fine with it. But after 550, my Google Doc lags a lot. That's why I said one 550. But I can deal with that. It's not a big deal. Anyways, with that said, I think I explained a little bit more than I should have. But next, we're going to do coefficient checks. Why are we doing coefficient matching? Well, think about it this way. 100 different constant lines will not never make a linear line. So these linear lines, no matter how many of these constants you put in here, you will never create this linear line. Therefore, they must match. Otherwise, this thing goes to nowhere, man, nowhere zone because it doesn't make any sense. It must match. Okay? That is how you get it. Anyways, with that matching, you finally get this and some oscillation happening here. And the full solution is a particular solution with the characteristic solution, as you would imagine, because this thing is just part of the solution. You still need the initial characteristics of the equation to activate to show what will happen in the beginning, no matter what you do. There are some parts to it. Otherwise, you here's your solution. There's your whole solution. You don't have to worry about anything. Anyways, we move on over here to the next question, which is cosine and we chose sine. I was going to do cosine sine, and you see, I designed this question really carefully here. I chose to say symmetric question 393 because it make it easier for me. Yeah, it would be harder if I didn't choose those numbers. Um, yeah, you'll see why, and that's why I didn't do a lot of cosine sine question. It's because it cancels out over here very easily over here, and it leaves us with this over here, which you can get into again, split the coefficient because there's no cosine here, and cosine must match with cosine because we learned that it's linear independent with Wolfskian, so they must match that way. Uh, doesn't matter how many sines you have. I mean, you can make a sine to cosine, but there's no phase here. So without the phase, no matter how many cosines you add up, it will never be a sine without a phase shift. And because there's no phase shift, we can definitely say that they're linear independent. Anyways, with that said, I can move on, right? I don't think I have to say anything else. This is what I chose. I took that, and this is at infinity. So again, I can take a derivative of that and plug into original ODE and pray to get the constants over here, and then plug it back in because at infinity it's going to be cosine wave or a cosine wave because it's a sine. Um, it's going to be a cosine wave, but you need to realize the constants must apply here, but it also must apply at the beginning. So using that idea we have gotten our initial. You see that the initial characteristic just makes a little bit more bump over here, and then it slowly goes to arithmetic regular oscillation, which makes perfect sense if you think about it. Uh, be, uh, because if you think about it for a second, what's happening here is that the initial mass spring activates, okay, and trying to make everything go to zero. It's trying, and it's failing. Um, yeah. And yeah, that's pretty much what's going on. Oh, another thing you should realize is that initial condition can be 0, 0, which means uh the position and velocity can be 0, 0 because of the forcing. Usually you can't have this. You can't have this. This is usually impossible if for a characteristic, but with the forcing it's possible. So you can jumpstart something at zero and boom, it out. It's like it's a it doesn't this initial condition that you need forcing to happen. Otherwise, if you didn't have this, basically what would happen if you get rid of this is that this with this initial condition will create a straight line like this, and then that's it. Boring solution. Doesn't make sense and it shows nothing. It shows absolutely zero. That's why you need that forcing. It's like a machine motor activating the system. And without that, you can't do anything. That took a lot out of me to say that. Anyways, mass with spring forcing is next. And over here, again, be smart. We have this over here. So we kind of knew how it's going to look at the end. It's going to look like this in the end. So with this, we can figure out the other constants. That's why I said there's a logical guess to this. It's looking at something at infinity and looking at that and said that will be what it is. And then saying, okay, I know what it'll look like at that point. Let's get the constant at that point and figure it out from there. Basically reverse tracking, and yeah, my professor did not teach me this in 20D. I understand why, but I wish he taught me. Um, because it's fun. I genuinely like this. Although it's very difficult, and I don't. I think you make a lot of algebraic mistake here, and I can understand that when you're grading this stuff. Oh yeah, everyone's gonna get a bad grade because look at this numbers. I don't think anyone will get a perfect score unless they have some kind of weird calculator that solves this and coded it up in there. But at that point, good job on you for coding that up. I actually probably find it online or something. I don't know. Um, anyways, over here you get over here. Basically the system is the hardest part, and to getting to co oh, did I talk about how you have to put the initial conditions again? Oh, I don't think I did. So these initial conditions, oh, not again. And this always happens to me. Like I always clicks on something that I'm not supposed to in this damn Zoom. Okay, it always happens. Always. Let's go to variation parameters so I can explain this a little bit better. So these conditions also play a part. I think I didn't talk about it because I talked about how there's these conditions over here that plays a part, but these initial conditions come back again in the very end over here to figure out everything. You cannot plug in the initial conditions when you only solve the homogeneous part. That would get you a wrong answer. Okay, clarifying that is a good idea. Anyways, we move on over here. And I already explained this pretty much, right? Yeah, this was a messy one because you have two different like systems. So you have exponential and a constant. So two different like guesses. Now very much primer I had to fix everything because I don't like how I changed how I did this. I'm gonna spend so much time fixing it. Um, this doesn't look bad, but it doesn't look good. Um, yeah, I'm gonna have to change everything. And this looks. What the fuck am I doing here? What the fuck is this? Oh God. Okay. Okay. Yeah, I'll fix this. Anyway, Laplace is the thing that's actually oh my God, that looks awful. Did I used to do it that way? No wonder it looks bad. I'm gonna have to change all that. Okay. Oh God. Oh God. Oh God, that looks ugly. Oh God, what is that? Oh my God, that looks ugly. Okay, there's a lot of things I need to change. I was a bad at making textbook and when I was in freshman year. Oh well.